Friends, next we discuss the inbuilt input and output functions in the language LISP. I have already explained the importance of the input and output functions in any programming language, because whatever marvelous computation a computer language may make provision for, if we are not out to give inputs and whatever the computer system has computed, it is not given to the user back in some form, the whole exercise by the computer system becomes useless. So what are the inbuilt input and output functions in the language LISP? We'll consider next. So please look at the slide. The input provisions in the language LISP, how to give data to the code of LISP to use, is through the read statement. Whenever a read surrounded by a pair of parentheses, whenever it is encountered by the LISP system, then during execution it waits for input by the user, and whatever any S expression can be given as an input during the read statement's execution. Once the user has given the input and returned the value, use the enter key, then the system further acts on the remaining execution part. So for example, in this particular case, we have given a statement in the language LISP as +7 read. Note the read statement is given by enclosing READ with a pair of parentheses. Suppose, so when the LISP environment executes this statement, first of all it evaluates the argument. The first symbol plus is executed as a plus operation. Then next its values are evaluated, and we know every number evaluates to itself, so 7 evaluates to 7. The second argument to plus is a read statement. So when the LISP system comes to the execution of this one, it waits for the user to give an input, and if the input is appropriate, it is evaluated, and after the evaluation the read word is replaced by the value supplied by the user, and the whole of the statement is executed. So suppose the user gives the value 8, then the execution of the initial statement +7 read takes the form +7 8, and +7 8 on getting executed returns the value 15. Friends, while giving the outputs, it is very important that the statements which are printed are given out by the system must be in an appropriate form, and blank lines also play an important role in the readability of the output given by the system. So ternary is a primitive command built in language LISP through which we can leave the current line and start printing on the next line. So ternary is nothing else but for leaving the current line and started printing on the next line. Now once read is already defined, next we should know how to output, or how the computer system's computation can be given in the format of output, either on the computer or on a printer. For that purpose, there are a number of commands. For the input, as we have just now discussed, we have just one command, namely read. However, there are a number of different shapes or forms of the outputs. We'll discuss some of those. Each has its own relative merits and demerits. In addition to the type of printing required, each is more appropriate as compared to the rest. So for this purpose, there is a command called print. Then we'll later on see there is a command print1. Then there is another command print, etc., etc. So let us start discussion of the various print commands which are output commands. So for this purpose, let's have a look at the slide. So on the slide, there is a, after the arrow, print quoted x, y, z, u. So we print is the function which is to be executed by the machine. And we know whenever a function is to be executed by the computer system or LISP environment, then whatever is its argument is executed. And generally when we want to print something, or when we want some expression to be written as its value, it has to be quoted. So print quote x, y, z, u. This means we want to print the left parenthesis followed by x, followed by y, followed by z, followed by u, followed by right parenthesis. Because we want to print it, but if we don't use a quote, then its evaluation will be different, because in that case x, y, z, u have to be evaluated, which must have been associated some values earlier. But we don't want the values to be printed, rather the list in which the x letter occurs, y letter occurs, z letter occurs, and u letter occurs. And these four letters are bounded by a pair of parentheses. We want this to be printed, therefore it is quoted. But you will see that when LISP environment executes this particular statement, it does not, it not only prints one line, but it prints two times the same quoted expressions after removing quote. That is x, y, z, u is printed twice. What is the reason for this? Reason for printing the evaluated value two times is that once the value is returned, as I mentioned earlier also, whenever an S expression is given for evaluation, its value is always returned. Even you might have noted that when the function define was given and define sum cube was defined, then at the end of the definition, even when the argument values were not there, the word sum cube or the symbol sum cube was returned. That is, whenever any S expression, whether it is a definition, then also some value is returned, and in the case of a definition, the name of the function being defined is returned. And in the case of print, there will be two actions taking place. First of all, the value will be returned, and second, the value will be printed. And therefore, instead of one time, it will be two times the returned value is printed. Please look at the slide. So you can see when the command print quote xyzu list is given, then xyzu is first line indicates that the value xyzu list is written, and second, the print command is executed, and print command demands us to print the list xyzu, therefore it is print. I hope this clarifies why there are two lines on the computer screen. The first line is corresponding to the value returned, and second line is corresponding to the print command. Friends, as I mentioned just now, for returning values, there are various formats. Each has its own shape of return values and its advantage also. I just now defined print command, and I explained that whenever a print command is executed, generally there are two lines which are of same values. Now there is a command print1. What is the role of print1? That in this particular case, in the case of print, please have a look at the slide. The XYZU lists are printed on two different lines. That is, after printing it once, the inbuilt system leaves that particular line and starts printing on the next line when the print command is given. However, in some of the situations, we don't want the current line to be left and to go to the next one. Rather, we like to print the values on the same line. How to achieve this? This is not possible with the print command. For this reason, print1 is used. So, first of all, we are using print command twice in a queue, print left, print quoted right. Then in that case, when this statement is executed or sequence of statements is executed, then first the left is printed. Then right is printed. But on the next line, however, when we give print 1, then in that case the left is printed and right is printed in sequence, but on the same line. That is, the current line is not given up for printing on the next line. So that is the difference between print 1 and print. There is another command for printing values, which is prints. The basic purpose of prints is that it does not, whenever its argument is double quoted, that is, it is a string, then in that case prints will actually remove the double quotes. So you can see prints good morning. First of all, good morning type, which is the value without quotes, but as I have already told that it returns the value and does the command good morning without quotes is the command execution of prints, and then the value of the argument is returned. So in this particular case there is a provision through which double quotes may be removed while printing. So that is the basic purpose of prints. So we have discussed 3 print commands. One is print itself, the other is print1, which does that, it continues printing on the same line, it doesn't leave the line, and third is prints, in which the double quotes may be removed. Friends, in the beginning, while discussing the characteristics of Lisp language, we mentioned that Lisp is a language which achieves its purpose of solving a problem through definition of functions which call other functions recursively or through others. So recursion is one of the most fundamental characteristic of language Lisp. Lisp is another very important characteristic mathematical property feature also, that a very lengthy definition may be summarized in 2 or 3 lines. So how Lisp, which recursion, which is a mathematical concept also, is realized in the language Lisp, this we'll discuss next. Friends, we know recursion in mathematics requires generally 2 steps. One is the recursive step and the other is termination step. We know if we don't give the termination step, then the recursion process continues forever. So we explain whatever I've just now said through an example. Please look at the slide. For example, we want to find out the factorial of a number n. So generally what we do, we know that the factorial n is equal to n multiplied the factorial of n minus 1. But the process will continue forever. So when we should terminate, first of all, suppose n is equal to 5. The next step will require computation of factorial 4. Next step will require computation of factorial 3. Still next will require us to compute factorial 2. Then factorial 1, then factorial 0, then factorial minus 1, factorial minus 2. Continue. This is quite dangerous and it will lead to the wrong answer also. So we must know when to terminate this process of finding out the successive factorials of values 1 less in each successive step. So we should know that there is a step where the actual value is obtained, which is quite easy to find out directly. For example, we know factorial 1 is very easy to compute. Factorial 1 is 1. Therefore, whatever may be the number given to us, say we are required to find out the factorial of 100. What we'll do? We'll say factorial 100 is equal to 100 multiplied by factorial 99. Then the recursive process requires us to find out the factorial 99 as 99 multiplied by factorial 98. Continue like this. At some stage we come to factorial 4. Factorial 4 is equal to 4 multiplied by factorial 3. Factorial 3 is equal to factorial 2 multiplied by 3. Factorial 1, factorial 2 is equal to 2 multiplied by factorial 1. And now we'll terminate the process because we know factorial 1 is equal to 1, and all these values now factorial 2 going in the reverse direction is equal to factorial 1 multiplied by 2, and factorial 1 is 1. Therefore 1 multiplied by 2, so factorial 2's value is finally obtained as 2. Now this value of factorial 2 is used in the definition of factorial 3 is equal to 3 multiplied by factorial 2. But factorial 2 now we know is 2. Therefore the factorial 3 becomes 6. Now this value 6 is used in the definition of factorial 4 is equal to 4 multiplied by factorial 3. So factorial 3 is replaced by 6. So we get factorial 4 is equal to 24. So going backwards by substituting the final values of a particular factorial in the computation of the factorial of one number higher, we can go up to factorial 100. So this is how. What is the advantage of recursion? That the definition becomes very simple. However, the recursive process sometimes requires additional resources, and in some of the situations we don't advise to use the recursive definition. Rather we prefer from executional point of view the iterative definitions, but that is another point. Here we are discussing how recursion is achieved in language LISP, and for that the earlier developed machinery of define, the earlier machinery of do, the earlier machinery of let, earlier machinery of count, etc. is used. So let us have it at the slide. Through some examples we explain how recursion is achieved in the language LISP. So the mathematical function factorial n, which is defined as factorial n is equal to n multiplied by factorial n minus 1, and finally factorial 1 is equal to 1. How it is translated in the language LISP? As I mentioned earlier, we will define the function factorial n, and we know how to define a function like this. That is, first of all, left and right bounding parenthesis will be there, then the define word is used, then the name of the function which we may call as fact, and then the argument n. What is the number whose factorial is to be computed is taken within parentheses as parameter. Here it is only single argument function. So now this is the part which tells the computer system through define we are defining a function. The name of the function to be defined is fact, and the argument list required by the function's definition is a single number which we denote by n. Now we know that from the definition as given at the top, if the given number n is equal to 1 itself, then we need not do anything else except return the value 1. However, if the n is not given as 1, then we will be doing the other process of computing it as n multiplied by factorial n minus 1. But initially we must check whether the given parameter n is equal to 1 or not. So here it is cond. Cond means that you check whether n is equal to 1 or not. If n is equal to 1, then whatever is the statement following it should be executed. N is equal to 1 condition, if it becomes true, then says that you should return 1 as a value, final value. However, if n does not happen to be 1, then the whole of the clause on the line given by equal to n1 followed by 1 is neglected. As I mentioned earlier also, that T indicates that this clause must be executed. T means true, that is, this is always true, and because whenever there is a condition is true, then the clause following it must be executed, because T always evaluates to true. Therefore whatever is following must be executed. And what is following it? Following it is that find out the product indicated by star of the given number n with the factorial of the number which is less than 1 of n. So it says that if n is not equal to 1, in that case you multiply n by the factorial of n minus 1. But in that particular case, what would happen? Now factorial n minus 1 may not be known. Suppose n is given as 5. Then the last line t star n factorial minus n1 indicates that the value of the factorial n, that is factorial 5, is equal to star 5 factorial 4. But factorial 4 is not a number, so it can't be given to the user. What will be done? That the factorial function will be again called by the LISP inbuilt mechanisms, but now with argument 4 instead of 5 earlier. And again it will check whether 4 is equal to 1 or not, and we know 4 is not equal to 1, therefore the value 1 will not be returned. Again we will come to t, that is this clause must be executed, and here it says that factorial 4 is equal to multiply 4 by factorial 3. Again factorial 3 is not known, therefore again the factorial function will be called, but this time with the argument 3. Now again the process is repeated, and ultimately we come to computation of factorial 2 is equal to factorial product of 2 multiplied with factorial 1. But we know through our earlier con equal to n1. Yes, n is equal to 1, and whenever n is equal to 1, the condition is true. Whatever are the following statements must be executed. The following statement says that the value 1 should be returned. Now this value 1 is returned to the computation of factorial 2. The value of factorial 2 is computed by using the value of factorial 1 as 1. And the process goes in the reverse direction, and ultimately we are able to find out the factorial of 5, which comes out to be 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, which comes out to be 120. So friends, I hope that it clarifies how the process of recursion is achieved by the language LISP. That is, first of all, condition is tested for termination. If the condition for termination is true, then the computation goes in reverse direction. However, if the termination condition is not true, then in that particular case, the next condition is found, which is always true, and the statements following it must be executed. Now, the statement generally is the translation in LISP of the mathematical definition, which is not the termination step. I hope the recursion is cleared. We take another example. In order to clarify how the recursion is achieved, we define another function, namely length of a list. That is, what are the number of topmost elements in a given list. I have already told that if there is one of the elements in the list is 2, 3, 4 list itself, then this list of 2, 3, 4 will be counted as number only one, contributing 1 to the length of the list. It will not be contributing 3 to the length of the list. So with this clarification, let us have a look at the definition of length, which is given over here to explain the concept of recursion. So friends, again we are defining a function length. We give the name len capital. In this particular case, the name of the function length is len, len. And define word is used to indicate that we are defining for the list environment the function len. And it will be taking a single list. So list will be a single list, will be its argument. So con. First of all, it may happen the list given to us is null. But how we will define the length of a list? The length of a list may be defined like this one. If the length is, if the given list is empty, then what will be the mathematical definition of the length of the list? 0. Any empty list has 0 number of elements within it, and therefore the length of an empty list can be very easily defined as 0. However, the list is not empty, then what will be the recursive process for computing the length of the list? What do? You remove the car of this. Then you will be getting a list with one element less. So what you do, you remove the car of this, you get a new list and find out the length of that and add 1 to that in order to get the length of the original list. And the process continues till we reach an empty list. So exactly this is translated in the language list as follows. Please look at the slide. The slide says that first of all you test whether the list is null or not. If it is null, then we'll be saying that the length of this list is 0. However, the second condition is always T. T means that it is always true, and therefore you compute the second step. And the second step says that add 1 and find out the length of the list obtained by taking the kudder, that is throwing out the car. We know that when the kudder is taken, the length of the list becomes 1 less of the original list, and therefore 1 is added in order to compensate for the length being reduced through the process of kudder. So this gives you the complete definition. Suppose a list has 3 elements, say 1, 2, 3. So first of all and the name of the list is L. Then first of all L, which is the list 1, 2, 3, is tested whether it is a null list or not. And we know the list 1, 2, 3 is not null. Therefore the next step is executed, that is T. T means must execute next step. And under the next step what we have to add 1 to the kudder of the list L. And kudder of the list, you know, is kudder of the list 1, 2, 3 is the list 2, 3. Again it is now length of the list 2, 3 is not number. Therefore again len is called, but this time is associated with 2, 3. Again the process is repeated whether it is a null list. No, it is not a null list. Therefore what is done, 1 is added to the kudder of the list 2, 3. That is 2 is thrown out and the length is found of the remaining list 3. And ultimately you know again list 3 having single element 3 is compared, found out whether the list is null or not. And we know the list 3 is not null. Therefore next step is executed where we find out plus 1 to the length of the kudder of L. But kudder of list 3 is equal to empty. And now at this stage we have L is associated with null value, null list, and therefore 0 is returned. And at every step successively 1 is added, and ultimately we will find out the length of list 1, 2, 3 will come to be 3. So I hope with these 2 examples it is clear to us how recursion is achieved in the language LISP. Next we take another function. Please look at the slides. Instead of sometimes we may be interested in not the topmost elements which may be lists also. We are interested in the number of symbols occurring in the list, whether they are occurring at the topmost elements of the list or they are elements of a list which is an element of the given list. For example, in this particular case at the slide you can see that actually the list has 3 elements, namely 1, then the second element is a list which has 2 and another list 3, 4 as its elements. And the third element of this list is 5, list 5. However, we want a function to be defined in which we get the answer as 5, where 5 is the number of symbols which are occurring within this list. How to define this? Because the length function doesn't do it. Length function will always return 3, which is a built-in function. How to achieve this? For this purpose we will have to look into another function which is defined in the next slide. Here what we will do, at each step we will find out the car L. Instead of adding 1, we will be adding the number of elements which are there in the car L, because car L, please look at the previous slide. Sometimes after removing one from the list will have two topmost elements, the first element of which will be 2, another list 3, 4, all making a list. Now, if we are using length function, then it will be returning 1 and we will be taking only the coulter. However, now we wish that our car contributes 3, which is the number of 3 elements which is in the list deeper and deeper. So how to achieve it? That instead of adding 1 instead of a particular element, we find out the elements in the car, find out the number of inside symbols in the coulter, and repeat the process at those. So this is exactly the definition of deep length, in which we are finding out number of symbols within a list and not the number of topmost elements. So friends, in this particular case, what is done, that is, first of all we test whether the given list is a list or not, whether the given S expression is a list or not. If it happens to be a list, then we'll find the car of this and the coulter of this and apply the deep length to the coulter and deep length to the car and deep length of the coulter, add those numbers, and ultimately we'll be finding out the total. However, if the car is not a list but it is a symbol, in that case very obviously each symbol is contributing 1 to the deep length and therefore 1 should be added. So here there are 3 clauses within the con. First of all, the list is tested whether it is empty or not. If it is empty, then the length of the deep length of the list is 0. However, if its car happens to be a symbol, then 1 is added, which is given by the last clause, but it is neither a null list nor its car is a symbol. Then in that particular case, we will find out the car of L, we will find out the coulter of L, we will find out the deep length of both car L and coulter L, and we will add those numbers. That will give us the deep length, that is the number of symbols occurring within this one. Friends, every language has to store, generally has to make provision for storing large data also, because databases are very frequently used for supplying appropriate data for finding out the solutions of the problem. What are the provisions in the language LISP for storing data and accessing it later on in order to use it in solving problems? So we will be discussing that, and for that we will be having the concept of association list, etc. So first of all, the involved ideas are explained through an example, and then we will discuss the structure for that particular issue of data storage. So please look at the slides. For example, we want to store the information about the authors of various books published at international level. So what should happen? We should have in our storage the title of the book, the author of the book, the year of its publication, and the name of the publisher in as one record instance. And for different books, we can supply these values for title, author, year, and publisher. And in this way, we can create a storage, data storage for future reference. What are the provisions in LISP to provide for this data storage aspect? So set Q is used. Set Q book. Book is the indicative of record instances are for books. So first of all, you can have a look at it. Everything is given within parentheses. So first parenthesis indicates that now we are starting with various attribute values which are associated with the book. A title is associated, an author is associated, an year is associated, a publisher is associated in this particular instance. So what will be the value of title is given within a list, or if it is a symbol, just as a symbol, as a second part after the attribute name. Attribute name is title. The attribute value is given within parenthesis LISP second edition. Similarly, attribute name is author. Its value is Winston and Horn. Attribute name is year. The attribute value is 1984. Attribute name is publisher. Attribute value is Edition Wesley. And this is the structure or construct which is used in LISP language to provide the information that the book under consideration is a LISP second edition written by the authors Winston and Horn in the year 1984, and the book is published by Edition Wesley. The structure, the construct is as given in the last 4 lines of the slide. I hope it is clear. So friends, as I have already explained, that in this particular case the book has 4 attribute names, namely the author, the year of publication, the publisher, and the title of the name. Now one thing is to give the data. For example, in this particular case we have stored the data. How to extract this back for the purpose of doing some computation? What are the constructs in language LISP for retrieving the value from the database which is already stored from the mechanism which I have just now explained using the setq command? So there is a function assoc which is given the attribute name in order to know the attribute value. So let us have a look at the next slide, the procedure assoc. For example, already we have in the database that LISP second edition is written by Winston and Horn in the year 1984 and published by Edition Wesley. Now we want to know what is the year of publication of the book. So the command is given at the last but one line. Assoc is used for this purpose. ASSOC. Then you give quoted year and the name and the book name, and it will return. Book was the name of the book. That year is 1984. That is the inbuilt system after retrieving the information from the database through the command assoc gives us the year as 1984. Now another way, property list. Friends, in addition to assoc, instead of, we can put the values directly also. So for this purpose, look at the slide. There is another command called putprop. Now what putprop does, for each attribute it uses one command. For example, putprop book list title. What is happening? That whatever is the entity, in this particular case book under consideration, the second is the value of the attribute name which is given as third argument. So LISP is the value of the attribute name title. So the syntax of putprop is, first of all we write putprop, then whatever is the entity under consideration, then whatever is the value, and lastly the attribute name whose value is given as second argument. So whatever information we gave through the setq may be also given through putprop, but at one time value only one attribute name can be given through putprop. So in order to give the title we use putprop book list title. Then to give the names of authors we give another instruction, putprop book Winston and Horn author, putprop book Edition Wesley publisher. That is first the entity book, the last the attribute name, and middle the value of the attribute name which is given as the last argument. So now, but while similarly we are giving the year, so putprop book 1984 year, which says the year of publication of the book is 1984, which is given as second argument of putprop. So a general definition of putprop can be seen that first of all putprop, then the object name symbol, then the attribute value, and finally the attribute name, which I have already explained to you. Now there is a construct set F. I have already discussed set Q. What is the rule of the set Q? That set Q must be followed by symbol, some symbol XYZ or any other lengthy symbol. And then a second argument is there, the value of which is found and associated with the first argument which is a symbol. So set Q x3 means that through this command we can associate value 3 to the symbol x. However, set Q can be used only for associating values to symbols. That is, the first argument of set Q must always be a symbol. It cannot be something like car of this. That is, for example, you are given a list of 3 elements x, y, z, and you want to associate value 3 to the first, that is car of the list x, y, z, that is to the x. So you cannot give a command something like that, set Q, then in the car of the list x, y, z 3. No, you can't. It is illegal. It is not appropriate syntax in LISP. So, but in some of the situations we require that we don't know the symbol with which the value is to be associated, but we know it occurs in some list or something like that, and car of that require, or some coulter of that require, and that is to be associated with some value. So set F provides mechanisms by which we can associate values which are not given as symbols but can be given indirectly through the operations of a list or some other operations. So that is set F is a more powerful construct for associating values. And for the further explanation, let's have a look at the slide. So slide says something like this, please. Slide says set F get book title list. What is the meaning of this? Actually, there is a command get also, which says the get the title of the book, and that is get book title only tells us that you have to associate some value with the attribute name title of the entity book, and that should be LISP. But major thing here worth explanation is that had it been set Q, then you could not have given a list as its first argument. That is very important. But once set F is there, you can give a list which may represent a function, and then the values can be associated. So here in this particular case, set F allows us to associate the value LISP to the attribute name title of the entity book. Similarly, you can do the rest of the functions which we have already done. That is, we may associate Winston and Horn as the value of the attribute name author of the entity book. So what we do, we say set F get book author, that is, associate the value of the author of the entity book as given by the second argument's value, and second argument's value is Winston Horn. Similarly, we can give the name value of the attribute name publisher of the entity book as Edison Wesley by using the command set F get book publisher quoted Edison Wesley. And even while setting up the values, the value returned is the value of the second argument. So friends, this explains the role of set F and get also. General form of associating values through set F is given on the first 3 lines of this one, which I have already explained. For further exploration, please look at set Q L X Y Z. Now you can see that the argument of set Q is a symbol. It cannot be anything else but symbol. However, set F can associate value to even car of this one. That is, car of L, which happens to be X, is associated with value A, and after this statement is executed, even X is replaced by A. So that is a major difference between set Q and set F. Friends, we will discuss some other powerful features of the language Lisp in our remaining lectures. So with this, I hope you must have learned a number of new features of the language Lisp. Thank you.